Okay, so we will continue chapter 4. So if you remember from before the break, we started with the first point. We start with the fundamental concept. We explained what is meant by reservoir, what is meant by reversibility, heat engines, how to calculate efficiency of these heat engines, and this efficiency is called thermal efficiency. Then we revised the reviewed the second law statements of the second law of thermodynamics. We have Kelvin-Planck statement, Clausius statement, and then we have a universal statement. We explained the statement itself, but we didn't explain where the statement came from. But this statement is relying on the definition of entropy. So today we will start to define what is meant by entropy, where this entropy came from, and how, based on the definition of the entropy, we ended up with the universal statement of the second law of thermodynamics. Okay. Then we will remaining 3 points. Hopefully you can cover any of them today. If not, this will be the content we have next lecture. So how the entropy is related to the disorder, how entropy related to the work loss, and finally the equation that describes the entropy balance. And then we have some examples. So now let's start talking about the entropy and how the entropy shaped the second law of thermodynamics, or ended up with a universal statement for the second law of thermodynamics. So far as we said we have a reversible process. When we talk about the reversibility, when we said if we have a reversible process, then the maximum work you can obtain from this process. If you have a heat engine, so the maximum thermal efficiency can be obtained. Like if you can operate this heat engine as a reversible one. Based on this, we have Kelvin. Kelvin, he defines like an absolute temperature scale. You know that the temperature, or the Kelvin scale for temperature. And Kelvin, he said something. Kelvin said, okay, if we have engine, and this engine operates in a reversible way, then I will have the maximum efficiency of this engine. So in general, I know that the efficiency is 1 minus QL divided by QH. This is the definition of thermal efficiency we explained before. So what Thomson and Kelvin said, they said, if we have an engine and this engine operates in a reversible way, then we can relate efficiency not only to QL and QH, the amount of heat like released and gained at the high temperature reservoir, low temperature reservoir, but the efficiency also can be related to the temperature of the hot reservoir, can be related to the temperature of the low reservoir at the same time. So we can say this efficiency, based on Thomson and Lord Kelvin, is function of TH and TL. And then they said this QL we will replace with TL, and this QH we will replace with TH, and then thermal efficiency we can express it as 1 minus TL, the temperature of low temperature reservoir, divided by TH, temperature of high temperature reservoir. So this is another way in order to calculate the thermal efficiency. So if you remember, so far we have 3 laws that we can use to calculate thermal efficiency. The first one, thermal efficiency is net work divided by Qn. Second one is what we have here, 1 minus QL over QH. Third one, 1 minus TL, temperature at low temperature reservoir, divided by temperature of high temperature reservoir. But the last case, this one, only we can use it if you have heat engine operate in a reversible way. The other 2 ways, or the other 2 models, or the other 2 equations, this can be applied in reversible or in irreversible way. So far as clear? So if you have heat engine, and in the problem I told you this engine operates in a reversible way, then you have an extra equation you can use in order to calculate the thermal efficiency of this heat engine. And usually this is much easier than, because you will have the temperatures, so there is no need to apply the first law of thermodynamics, no need to do any energy balance to find work or to find the Q. Just you have the temperatures, substitute the temperatures in the equations, and then you can obtain the efficiency. Clear? Okay. So this is one way we have here, and again, this, or everything we are saying here, the relationship between the amount of heat and the temperature of the reservoir, this is only valid for ideal process. This is only valid for reversible process. Okay? So if we have heat engine, and again, this heat engine is reversible, then we can assume QH over QL. This is TH over TL, and you can calculate thermal efficiency based on temperatures. This point is clear? Okay. One thing to remember about the heat engines, we said heat engines operate in a cyclic process, right? So cyclic means you end up at the same initial condition. So if we need to make a plot, for example, for any properties we have, so if we have property B on the y-axis, property A on the x-axis, so let's assume we start here at this point. So we have one process, we have changes happen to the system from case 1 to case 2. Then we have other changes happen to case 3. Then we have changes happen to case 4. And at the end we have changes happen to return one more to case 1. So 1, this is your initial. And at the same time, this is your final. So this is why here, if we have this happen, so we said we have cycle. One of the characteristics of the cycle, if you need to calculate the change you have in any property for the whole cycle, this change will be 0 because you end up at the same initial condition. So what is the temperature change for the whole cycle? 0. Because state number 1, this is your initial condition. At the same time, this is the same as final condition. The pressure change will be 0. The internal energy change, enthalpy change, entropy change. So the change of any property for the whole cycle, this will be 0. Okay. This simple rule help us to have the first definition of the entropy. So if you start from here, starting from this slide, you will see a lot of math. I don't ask you to memorize this math. I will not ask you to derive it. Just if I'm a student and I need to end up with a certain conclusion, I prefer to see the math behind it. So you will have the detailed math, okay? I will try to explain the findings of this one. But when you are studying, if you need to do the derivations or you see the detailed calculation of this one, so everything is you can find in the slides. So here in this one, if we have a heat engine, and we said if we have reversible heat engine, so we can make use of this relation, that QL over QH is the same ratio as TL over TH. Or if we arrange it, Q over T for the low temperature reservoir is Q over T for the high temperature reservoir. If you analyze everything that happened in terms of the energy transfer for the heat engine, then you will see that for the reversible heat engine, QL over TL plus QH over TH, this will be 0. The same amount of heat that the temperature gain is the same amount of heat that the temperature will reject at the low temperature reservoir. And because of the sign convention, so we have here QL, one of them is Q gained, one of them is Q lost. So you have a sign convention which is positive and negative. Heat added to the system is positive, heat removed from the system is negative. So we can end up with this one here. The last slide we said the change of any property of for any cycle, this is equivalent to 0. And in heat engine, you have Q over T for the low temperature reservoir plus Q over T for high temperature reservoir, this is equivalent to 0. Then we can say the integration for the whole cycle. This circle here means we make integration for the whole cycle. So if you integrate the change we have in Q divided by temperature, this will be equivalent to 0. Again, what we said, the integration for any property for a cycle, this is equivalent to 0. Then when people see this observation, when they see these two equations, then they said, in general, we know that for any cycle, change of any property for the whole cycle is 0. When we analyze the heat engine, we can see that the change of Q divided by temperature over the whole cycle, this is 0. Then we can assume that Q over T, this represents a certain property. So from this observation, from this comparison of these two observations we have here, then we ended up with this conclusion. Q over T, this represents a property. What is this property? We will call this property as entropy. And this was the first definition of entropy. Okay, and this is how entropy initially came from. So entropy came from there's a conclusion that the change of property for the whole cycle is 0. When we make analysis for any heat engine, we found that Q over T for the whole cycle is also 0. So Q over T, this is equivalent to a property. This can be a property describe the system. What is this property? We will name this property as an entropy. And what is the definition of entropy? So far there is no definition. Okay. At this stage, when they defined entropy, the whole definition is that this is a property of the system and it's calculated by Q divided by T, and that's it. But there is no physical meaning for it. Okay, so far it's clear? Okay. Now we try to analyze the heat engine to see the entropy and the temperature change in this one. For the heat engine, we have two like reservoirs. One high temperature reservoir, which call it heat source, low temperature reservoir, which is the heat sink. If you calculate the temperature difference at the high temperature reservoir, so we have the source is giving heat to the working fluid, so delta T is temperature of the source minus temperature of the working fluid. If this process is reversible, so this delta T will be very small because the driving force for reversible process is very small. So the driving force is very small, almost zero. Irreversible process, we have significant, like delta T, significant driving force. So we can say for the, at the heat source, if you need to find delta T, temperature difference between the source and the working fluid, this is always equal or greater than zero. Okay, it will be equal to zero if the process is reversible, more than zero if the process is irreversible. Same thing for the heat sink. So for the heat sink, if you need to find temperature difference for the heat sink, this is the temperature of the working fluid minus temperature of the sink. If the process is reversible, so the delta T will be small or large? Small. Any reversible process, the driving force is small, close to zero. So if you have the reversible process, so this temperature difference will be small. Large or irreversible process, so delta T is more than zero. So if you have heat sink, delta T is also greater or equal to zero. So this analysis, this slide tells you in the heat engine, the temperature difference at the source and at the sink, it will be greater than zero. In the ideal case, it will be equal to zero. It can't be negative. Okay, so any temperature difference in heat engines, it's greater than zero, or in the ideal case, in the reversible case, this delta T will be zero. Okay, how this with the definition of entropy can shape the universal statement of the second law of thermodynamics. Let's finish writing. Anyone is writing? Okay. Good. Now, again, there is no need to memorize all of these things, okay? But what I'm trying to do here I'm trying to see how the entropy will change in the source and at the sink. In order to study the entropy change at the heat source, then I need to consider the entropy change for the source and the entropy change for the working fluid. If I need to make entropy analysis at the heat sink, then I need to see the entropy change for the sink, the entropy change for the working fluid. And what is the entropy? Delta S is Q over H. So Q over H for the source, Q over H for the working fluid. Q over H for the sink, Q over H for the working fluid. If you consider the sign convention, any Q that is added to the system is positive, any Q removed from the system is negative, then we will end up with this equation. So delta SH entropy change for everything we have in the reservoir will be this equation. And again for the sink, we will have this equation. So in this equation, you will see temperature of the source minus temperature of the working fluid. Here you will see temperature of the working fluid minus temperature of the sink. These are delta L we presented in the previous slide. And in the previous slide we said this delta T, either at the source or at the sink can be negative. No, it's always positive. In the special case, it will be equal to zero. So this is why, based on this observation, we can say entropy change for reservoir or entropy change for the sink. Also, this one will be like positive, or in the reversible state, it will be zero. So again, so far we defined where entropy came from. It's a property we have for the system. And this entropy is Q over T. Then we analyze temperature changes for the whole system at the source and at the sink. And we found that temperature change is positive. If you have like the ideal case, the reversible case, delta T will be very small, approximately 0. When we combine these two observations together in order to analyze the entropy change for the reservoir and for the sink, so we ended up with the same thing. Entropy change for reservoir for the source is more than or equal to 0. Entropy change for the sink is greater than or equal to 0. So always for any heat engine, for any process we have, the entropy change is always positive. Entropy change can be 0 in one case, if the process is ideal or if the process is reversible. And again, we cannot have any reversible process in real life. This is only an approximation to simplify the analysis, to find the maximum work we can obtain, the maximum efficiency of the process. But in real life, the entropy is always increasing in the positive direction. Entropy always increase. Similar to, let's say for example, or let's keep it when we describe the second definition, because this will be difficult right now. So again, from this slide, this is what you need to understand. The total entropy change for any system, for any process, is greater than or equal to 0. In real life, in all applications which is irreversible, we have positive entropy increase. If you have a process is irreversible, ideal, then we have no entropy change. Now, if you remember this slide, you remember this example when we said we will put like a big mass on the piston, or we will make small tables. So this one, if you put just one big mass one time, this process is an example of irreversible. If you have very small balls and you put one by one, then you will have an example of reversible process. If you will make the entropy change analysis for this one, delta S, so you will see for irreversible process, the delta S will be positive. For the reversible process, delta S will be 0. And these are the two examples here. So delta S is positive for irreversible, delta S is 0 for reversible. So far it's clear? Any questions? And this led us to the second law of thermodynamics, the statement of the second law of thermodynamics, which says for any process to take place spontaneously without any external assistance, delta S total should be greater than or equal to 0. This statement, it combines hundreds of statements describing the second law of thermodynamics. It describes what Calvin Planck statement. It describes what Clausius described in his statement of the second law of thermodynamics. So just one statement describes the second law of thermodynamics in terms of the entropy change that can be represent all the other statements that we have. Okay, so this is the universal statement of the second law of thermodynamics. Previous slide, we showed the logic behind like these things, why the delta S total is greater than or equal to 0. And this is the summary we have. So entropy, this is a state property, Q over T. Entropy, if the change we have entropy is depend on the process type. If we have reversible process, so the entropy will be unchanged through the process. If you have irreversible process, you will have an increase in the entropy. The entropy will increase and the change of it will be positive. So far it's clear? So this slide, this is a summary of all the other things. Okay? It combines everything that we need to say in this first point. Questions? Clear? Okay. We have some perspectives to entropy. The first one is relating entropy to spontaneity and directionality. So what we said so far, let's put everything here. Let's see. What we said so far, so we have a universal statement of the second law of thermodynamics. In this statement, it says the process to occur spontaneously, then the entropy change should be positive. So now the entropy, it's related to the process is a spontaneous or no. And this is the shortcoming we have in the first law of thermodynamics. Do you remember? First law of thermodynamics, we said it's related to the energy transfer, energy conversion from one form to another form, but it doesn't give you any idea of the direction of the process. So this is why if you have hot cup of coffee, if you leave it in the table for some time, the temperature will decrease. This is consistent with the first law of thermodynamics. If you get cold coffee and you put it on the table, the temperature will increase. This is also consistent with the first law of thermodynamics. But the second law of thermodynamics, here he puts you some limits. It tells you, okay, the first option, the first one, the first process, this is possible to happen spontaneously. If you get hot coffee, its temperature will decrease because this is consistent with the second law. So if you fulfill the first and second law of thermodynamics, the process will occur. But if you violate any one of them, the process will not occur. And this is why here the definition of entropy, this one is described the direction. The process is spontaneous or not. And also we said so far the entropy we have for the universe is increasing. So according to this one, if we have a spontaneous, irreversible process, we have the entropy change is more than zero. Any process with negative total entropy, any process have total entropy change is less than zero, this is not spontaneous. This process will not happen by itself. It can occur, it can happen in case you have external intervention. But without any external intervention, without any external force to push it to occur in the direction that you want, just if you leave it spontaneous, this process will not occur. Okay. And what is delta S total? So delta S total, again, this is delta S of the system plus surrounding. So if you need to see this process will occur or not, then you need to see the entropy change, or calculate entropy change for the system, plus entropy changes for the surrounding, sum both of them to calculate total entropy change. If this total entropy change is zero, so this means that the process is ideal or reversible. If the entropy change is positive, this means this process is spontaneous and will occur by itself. If you just leave it, it will occur spontaneously. If the total entropy change is negative, this means this process is non-spontaneous. Clear? Okay. Let's see an example to this one. This example says we have piston cylinder device contains liquid vapor mixture at 300 Kelvin. During a constant pressure process, 750 kilojoule of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during the process. Here he need to find the temperature change of the water. Okay, not the universe, not the total, only for the water. So if you have this example, and let's assume I have this piston cylinder, and here I have liquid vapor mixture. So let's assume I have liquid and then I have vapor here, and this is the surrounding we have. So this is my system, this water is my system, and he need to find the entropy change for water. You need to find entropy change for my system. And what he says, we have this system at 300 Kelvin. We have phase change process happening. Phase change for pure substance occur at fixed temperature, constant pressure. So there is no change will happen to this 300 Kelvin. And then we have an amount of heat added. And this amount of heat is 750 kilojoule. So the simple thing, if you need to find the entropy change for this water system, so we have delta S is Q over T. The amount of Q is 750. This amount of Q added to the system or removed from the system? Added, so it's positive or negative? Positive, we'll leave it positive. Then divided by the temperature. Temperature is constant, also in this example. Then we can substitute in this one, and we say delta S is 2.5, and the units will be kilojoule per Kelvin. And this is what we need to find. Just very simple. Substitute in the equation, calculate the entropy change. Clear? So now, can we say, because of delta S is positive, this process is spontaneous? Can we say this conclusion? Yes or no? Anyone say yes? Delta S is positive, so the process is spontaneous. Okay. No? No idea? Okay. Let's get back to the one. Here we said, if delta S total is more than zero, the process is spontaneous. If less than zero, the process is non-spontaneous. Okay? So according to what we have here, delta S is 2.5 kilojoule per kilogram positive. So can we say this process is spontaneous? Yes or no? Yes? Yes? Yes. Okay. The action is we can say yes, we can say no, because get back to the slide. Here, which delta S is more than 0? Delta S what? Delta S total is delta S of system plus delta S of both of them. Okay, if we get back to this slide where we explained, we have this picture. Yes. Here in this slide, the delta S total is positive, right? This delta S is summation of system plus surrounding. System is positive, surrounding can be negative. Okay, here we have system is negative, surrounding is positive. So again, you don't focus on the changes or the entropy change for the system, nor the surrounding, the summation of both of them. Okay, when you calculate delta S total, then you can make your decision. So here in this example, if we get back to it, here in this example, I said here I will calculate delta S of water, and water is my system. So this delta S I have, this is delta S of my system. I have no idea what is the delta S of the surrounding. Delta S of the surrounding can be less than 2.5. Delta S of the surrounding can be negative 3, for example. So if it's negative 3, so negative 3 plus 2.5, this is negative 0.5, then the process is not spontaneous. Okay? So the decision is based on the value of the total entropy change, not the system entropy change, not the surrounding entropy change. Clear? Okay. So now this will take us to the second example. This example says we have vessel A. Vessel A contains 0.1 kilogram of water, which is equivalent to 100 gram. Initially at 335 Kelvin, 80 degrees Celsius. And vessel B contains 0.05 kilogram, 50 gram, at 293 Kelvin, 20 degrees Celsius. They are brought into contact, as shown in this figure, and allowed to reach equilibrium. Find the final temperature of water and the change of entropy of the universe. We will focus on the entropy change in this one here. Okay. So the final temperature, just let me give you this information. This temperature is 333 Kelvin, and the final temperature 333 Kelvin. So we have the final temperature. Then we need to find the entropy change of the universe. This is the total entropy change. So total entropy change, universe entropy change, they are the same thing. Find the entropy change of the universe, assume the heat capacity and the specific water is this value, there is no heat exchange with the surrounding occurs. So we have this example here. Then what we need to find, we need to see what is happening. Here we have two vessels. So vessel 1, this one can be the system. This vessel is affected by B. He said in the example, there is no heat exchange with the surrounding. So this surrounding is not affecting the whole process. Only these two vessels are affecting each other. Okay. So if you assume that one vessel A, this is the system, then vessel B, this will be the surrounding. If you assume B is the system, then A will be the surrounding. So if you need to find the universe entropy change, so this will be the entropy change we have occurs at vessel B, A, plus the entropy change we have at vessel B. And based on this value, we can know the process is spontaneous or not. Okay. So again, ds is dq over T. This is the equation we have. Here we have exchange of heat between the two vessels. Temperature is not constant in any one of them. The first vessel start at 353, end with 333. Second one 293. So here the temperature is 333. So what we do in this case, we recall the first law of thermodynamics. So this system is open or closed? You have any mass in or mass out? No. So this system will be closed. So the first law of thermodynamics, this one will be du equal dq plus dw. So if you arrange this equation, we need to have dq, then dq, this one is du minus dw. Okay. And then we need to calculate each one of them. So dw, if you remember from chapter 1, I think, chapter 1, dw, this one is pdv. And if you recall chapter 2, we have du, this one is n cv dt or m cv dt. So we have the work equation, we described it chapter 1, and internal energy equation and its relation to heat capacity, this is from chapter 2. In this example, we don't have any volume changes. We have closed piston. So we can say that the work, this one will be 0. Because we don't have any changes happening in the volume, constant volume process. So we can say that dq is ncv dt or mcv dt. Okay. So which one of them you will consider? So get back to the problem. Here in the problem we have CV and CP is given 4.2 kilojoule per watt per kilogram, which is mass. So this is why we will cancel this one here. We will take the mass like basis equation. So we can say dq is m cv dt. So now this is dq equation, sub in ds equation. Then we can say ds will be m cv dt divided by t. Make sense? Any questions so far? Now we can integrate this one. Then we can say delta S. This one will be integration of m cv dt over t from t1 to t2. This is a closed system. We call the conservation of mass. The total mass will be constant or will be changed? Total mass will be constant for closed system, so we can take mass out of the integration. In the given, CV is number, is constant. We can take it out of the integration. So this one will be CV integration from T1 to T2 dt over T. So we make the integration, this will be M CV, then T2 over T1. So this will be the equation that we will use to calculate the entropy change. One time for vessel A, one time for vessel B. So far it's clear? So now let's put the numbers. We have vessel A. The mass we have in vessel A, this one 0.1 kilogram. Let's get the numbers here. So we have the mass is 0.1 kilogram. CV, the heat capacity is 4.2 times 10 to the power 3 joule per kilogram Kelvin. T1, this 353 Kelvin. T2, 333 Kelvin. So now we have everything. Just put this number in the equation. and then you can find the entropy change for vessel A, and this one will be 26.9 joule per Kelvin. And this is the first requirement we have. So this is the amount or the value of the entropy change we have of the system. So again, can you consider this value and say the process is spontaneous? No, because we need total entropy change, not system, not surrounding. So now this is what we did for the system. We can go to vessel B. So for vessel B, we have mass is 0.05 kilogram. CV, same, 4.2 10 to the power 3 joule per kilogram Kelvin. T1, 293 Kelvin. T2, 333 Kelvin. Now we have all of these numbers, substitute in the equation to find entropy change for vessel B. This will be negative 24.5 joule per Kelvin. Now use both numbers to calculate delta S total, which is delta S of A plus delta S of B. Now if you put both numbers, this number will be 2.4 joule per Kelvin. So now we can say we have this number for delta S total. So based on this number, we can say we have a spontaneous process. So which means if you have two vessels, the first one contains 0.1 kilogram water at 353 Kelvin. Second vessel has 0.05 kilogram water at 293 Kelvin. If you bring these two vessels in contact together to affect each other and just leave them without any interference from you, any action from your side, then by themselves the temperature of both vessels will decrease and both of them will be at equilibrium at 333 Kelvin. This is what is meant by spontaneous process. Just bring them together to affect each other and then the process will occur spontaneously. Clear?
Where was can you go back to your work to find that it was 333 Kelvin? Or was that just given?
Yeah.
In the original problem statement?
In the original problem it was one of the required, but it's a very long process.
Okay.
And I need to focus on what is happening in the entropy. So this is why when I read the statement, I said, assuming that it's given this one. In the textbook, you will see how this is calculated. Okay. Any questions? Okay. So again, for this one, as we said, for spontaneous process, if both tanks you bring them at 353, 293, so both of them will be in contact, so the temperature for both of them will be this one. But if you bring the opposites, if you have two tanks, 0.1 kilogram water at 333, 0.05 kilogram at 333, this is not possible that you will see vessel 1 increase to 353, the second one decrease to 293. So this is the description of the second law of thermodynamics. If you calculate delta S total for this one, which we calculated now, this will be 2.4. If you have this process, if you calculate delta S total, it will be negative 2.4. They have the same entropy change, but this one is negative, so this process is not possible. Clear? So far, what we have known about entropy. That entropy is a state property. And how we calculate it? It's Q divided by temperature. The change of this property for a cyclic process, this is equivalent to 0. The change for this process for any process is reversible, ideal, is also 0. But for real devices, the change we have for this property should be negative, should be positive. Okay. This continue until we have Boltzmann. I think in the first lecture we talked about Boltzmann. So Boltzmann, he came and he defined an equation. So this equation, as we said, it's on his tombstone. And Boltzmann said, okay, so what we know about entropy, this is not the everything that we know about it. We have other things to know about entropy. So what he said, this is what we know so far about entropy. Then he introduced the statistics into thermodynamics. He has applied something called statistical thermodynamics, and he said, we need to look to the microscopic view of the entropy. And based on this microscopic view, he ended up with an equation to say the entropy is Boltzmann constant ln this sigma, and this sigma is number of microstates. And he is the one that he said that entropy is measure of the randomness or disorder we have with the system. And this is the definition we have right now. If you just Google what is meant by entropy, this is the definition you will see. Just you need to go deep in research to see the original definition, which is a state property divided by or defined by Q over T. Because now this is the most common definition we have about what Boltzmann says. And what Boltzmann says, very simply, he said, what is the possibility we have for the location of the molecules? So let's say, for example, if I have this square, and in this square I have 4 sides. So here I have molecule A, molecule A, molecule B, molecule B I can have here. So how many changes in these microstates you can have? So you can put A at any of these sites, B at any of these sites. So we can have like A here, and you have B here in this site. This is number 1. And this is number 2. This is possibility number 3 of rearranging the molecules. This is number 4. This is 5. This is 6. So this is the sigma we have in the Boltzmann equation. This will be 6. This is what means number of microstates, the possibility we have. So you can see the molecules in this one. So this is what he introduced the statistics, the possibility theory in order to define or find an equation to describe entropy. And this is where the definition of randomness or disorder came from. Okay. Again, we will not go deep in this one. Even I won't ask you to count these things, but I want you to understand the where this came from. So now we have 3 phases for any substance. We have gas, liquid, solid. So again, if we see the randomness, so which one you think is more random, gas or liquid or vapor? The molecules movement in gas. So this is why entropy of gases, you will see it more than liquids. And entropy of liquids will be more than solids. So solids, this one has the lowest entropy because we have strong forces between the molecules. The motion of the molecules is hard. Liquids, we have weak forces. We have like more molecule motion can happen, so we have more entropy. Gas, we have a complete random motion. So when you hear this, we have randomness in the system, so means we have high entropy. Another thing, if you have any system and you increase the temperature of this system, so increasing the temperature means you are increasing the kinetic energy of the molecules, so this means you are increasing what? Entropy. The other side, if you are decreasing the pressure, decrease the pressure means you're having expansion. So you are increasing the distances between the molecules, so you are reducing the forces between the molecules, increase the random motion we have, so entropy increase. So entropy increase with increasing the pressure. Entropy increase with entropy increase with increasing temperature. Entropy increase with decreasing pressure. If you have mixtures, so let's assume if you have 3 gases, you have oxygen and you have an entropy for this one. You have nitrogen and you have certain entropy for this gas. You have carbon dioxide and you have entropy for this one. If you mix these 3 molecules together to have mixture, then what you will see that the entropy will increase. So the mixture that you have from oxygen, nitrogen, carbon dioxide, the entropy for this mixture is more than the entropy of oxygen alone, plus entropy of nitrogen alone, plus entropy of carbon dioxide alone. Just put everything together, increase the randomness you have, then the entropy will increase. So according to the phase, entropy of gases more than entropy of liquids, more than entropy of solids. If you have 2 substances at different pressures, the one with higher temperature has more entropy. 2 substances, even same substances at different pressures, the one with the lower pressure has the higher entropy. if you have different substances and you mix them, so the resulting mixture will have entropy more than the summation of entropy of each component alone. Okay, clear? Any questions?